Okay. Hello, everyone. Thank you for being here. This is the DigiQ Journal Club, and this is our session two on the topic quantum computing for plasma physics. Our speaker today is Óscar Amara, who is a PhD student at the University of Lisbon. And without further ado, I will just pass it on to you, Oscar. You can introduce yourself and just start the presentation.
Sure. Okay. Thanks a lot. So thanks for the invitation and for the introduction. So I'm Oscar, PhD student in my final year of the PhD program here at the Instituto Superior Técnico of the University of Lisbon. And I'm working in the intersection between quantum computing and plasma physics. Um, so I'll just very briefly try to explain what plasma is, at least for what concerns us. Here you have like an image of a plasma ball, and it's basically you can think of it as an ionized gas where we have charged particles and the fields, the electromagnetic fields that they produce and they interact with. So this collection of particles and fields can have very complex dynamics, and we're interested in studying these plasmas because they have many applications, both from industrial process to space weather and fundamental physics. And I'll try to explain why I care about quantum computing to study plasmas. And this work is based on this paper that you see here, published in the Journal of Plasma Physics. And I'll try to explain the ideas behind this. These are my collaborators at PhD Supervisor, and this is the team where I work in, so a subgroup within GoLP in Lisbon. Also, feel free to interrupt me and ask questions as we go along. You don't have to wait until the end. Okay, so let's get started. So specifically, I'm mostly interested in a regime of plasma physics, which we call extreme. And by extreme, we mean with extreme electromagnetic fields. It could also be extreme pressures, etc. Why? Because these plasmas or these physical systems exist in the region of parameters where we really don't have a very well-defined theory to describe them. We know that they exist in outer space, for example, close in the vicinity of pulsar magnetospheres, where the magnetic fields can be very, very high, and this can lead to the spontaneous production of electron-positron pairs in a regime of quantum electrodynamics that we call strong field QED. So these happen in space, but because of the technological advances in intense lasers, and you can see here on the right a small timeline of how the laser intensity has evolved with time. And you can see here that this knee here, CPA, chirp pulse amplification, this actually led to a Nobel Prize some years ago, the invention of this technique. As the intensity of these lasers increases, we can explore higher and higher fields in the lab that kind of mimic these plasma environments in outer space. Specifically these regimes of strong field QED. Now, in terms of computing power needed to simulate these systems, this is already a bit outdated, but I think the general picture is still valid that, lattice quantum chromodynamics is one of the biggest users of HPC resources, but plasma is not that far away, at least according to this metric. Of course, weather simulations are also very important, and other fields also use a lot of computing power. So it is in our interest to explore other ways of doing computing that could be efficient. And although we're still in the early stages, quantum computing could be one such venue for computing. The idea is that at least maybe in the next decade, we will have powerful enough quantum computers that we can actually start to offload some of the computing from classical HPC to these quantum systems. Um, okay, so um, you probably already know what digital quantum computing is, but just to be more or less on the same page, it's another way to perform computation. It's conceivable that, and people are already working on this, for example, at the Barcelona Supercomputing Center and others, where we have a heterogeneous collection of processing units, CPUs, GPUs, and QPUs in a cluster. And then, so these different devices are specialized for different tasks. And of course, what we want is kind of precision physics. Like in high energy in particle physics, they want to compute things to very high accuracy. Would be very nice to do this with plasma physics as well, using the most advanced computing technology. Quantum computing allows for this exponential compression of information in a way. This is, of course, hand wavy, but we can encode exponentially many more amplitudes for a certain number of qubits, and also for the subfield of plasma physics that concerns us the most. There are many aspects of plasma physics that are closer to actual quantum mechanics than you might think. Fusion is for the most part classical plasmas, but there are other areas where we could explore these quantum phenomena in plasmas. So the question is, like, how soon can we actually start using quantum computing and compare them with the classical codes that we already run on classical HPC? So yeah, that's the promise, but is it, are we sure that we can actually get some advantage with quantum computing? One of the major problems is that in at least in classical plasma physics, many processes are non-unitary, and so they don't map naturally to digital quantum computers. We have to think of some mapping. We have to either linearize the problem, or if the processes are dissipative, we have to maybe find a larger space, a Hilbert space where we can perform these operations, etc. But it's not native. This is in contrast to, for example, condensed matter physics or particle physics, where it seems more natural to perform those quantum simulations of quantum systems. And to add some more problems to this, we are in a stage where quantum computers are still not fault tolerant, they're noisy. So our idea was to think of some NISQ-friendly method that can be tried on current devices. And one such class of algorithms is the variational quantum eigensolver, which so in which this work is included in. To give you a better feel of why or what has been done and what is lacking. Essentially, as I said before, plasmas are this collection of particles and the fields that they produce and interact with. So there are some studies, some papers on simulating each of these components separately. Let's say that, for example, Maxwell's equations in vacuum. This has been done with quantum circuits already. This is just one example. There are others. People have already studied this very, very standard plasma physics phenomenon of Landau damping. But this is, of course, a small, very small number of qubits. And there is no self-consistent update of the interactions between the fields and the particles, because this is nonlinear. So it's not obvious how to map this to a quantum computer. So I would say that this is still underexplored, but this is a problem that we will have to tackle in the future at some point. So to explain the variational method that we use in this paper, I'll start very fundamentally. So you might recall from either the first or the second course on quantum mechanics, the variational principle. And at least in its simplest form, it can be used to obtain ground state approximations for some systems, either in chemistry or material science. And this is applied to the time-independent, let's say, single particle Schrödinger equation to make it more simple. And then we will generalize this to time-dependent. So the vanilla example would be this. We have a Gaussian wave function in one dimension, and we have a quadratic potential. What is the width or the spread of this wave function that actually minimizes the expectation value of the energy? And you can do this fully analytically. So let's say that this wave function psi is a function of x, the coordinate, but also of this variational parameter sigma, which we pretend we don't know its value yet. So we can write this functional form. Then we apply this operator, the Hamiltonian, to the wave function. We can compute the expectation value of the energy. And this is now a function only of this variational parameter. And we've already integrated out the coordinate. So this is now a function of sigma. And you can check the minimum exactly occurs at 1 for an energy of 1/2. And if you were to do this for the excitations of beyond the ground state, you would see that it exactly matches the quantum harmonic oscillator. So this procedure we will now use to the time-dependent formulation. So let's do another simple example. Let's do the heat equation in 1D again. So this is this linear, very simple partial differential equation, which has this first order time derivative, and this second order spatial derivative. So, and with this initial condition. So what you can do is, okay, you guess, if maybe you already know, that the solution will be some kind of Gaussian with a width that increases with time. So let's say that this width is parameterized by this variable kappa, k, in this way. So now instead of having the wave function, we have this this heat function u, which is a function of the coordinates t and x, but also k. So we can write it in this form. Okay, we can also introduce another parameter, the amplitude of this wave function, let's say. So now we have two parameters, a and sigma. And so basically, now we rewrite this as the time derivative of this variational ansatz is some linear operator applied to the ansatz. So here we have again, and what we will try to obtain is this system of coupled ordinary differential equations for the variational parameters. So essentially, with this method, we're trading a partial differential equation for a set of ordinary differential equations. And these objects, M and V, are respectively a matrix, so an object with two entries, and then a vector. And you can compute these through these inner products. So M, the matrix, only depends on derivatives of the ansatz, while the vector V depends on the linear operator that we are actually using. In this case, it's the heat kernel. So so we can obtain these explicitly in closed form. So essentially, this is the system of ODEs that we have to solve. And they are separable, essentially. So you can solve them analytically. And uh, at last, you get that the spread of this wave function scales with square root of t, as expected, and the amplitude as the inverse. And if you were to compare it to the analytical solution, this method, which we call variational quantum imaginary time evolution, VARKite, exactly matches the expectation. Okay, so this was kind of a tunnel. So now the idea is, because we can encode 2 to the n complex amplitudes with n qubits, if we find a variational ansatz with a number of parameters L that is very small, much smaller than 2 to the n, then we can essentially parameterize efficiently this wave function. And so in principle, this should be a good trade-off, a good compression of information, essentially. And again, these are the inner products that we have to compute, and so on. So basically, on a classical computer, we would only have to store L parameters and update them in time instead of 2 to the n amplitudes. So what we apply this idea to simulate essentially an equation that is very similar to the heat equation, which I'll show in a moment, where we expect the solution to be very close to some Gaussian wave function. So again, this is very simple. This is also a toy model, but this is a proof of concept to further generalize. So the idea is that the specific ansatz that we used is this one. So we're only using RY rotations and C naughts to make sure that the amplitudes are real valued. This was just a choice because we could have chosen other mappings that would include complex amplitudes, but this is the simplest one. So essentially, this variational block in blue will produce some wave function, and then the red block enforces some even symmetry of the wave function. Essentially, these two blocks combined, the blue and the red, always produce symmetric functions, symmetric in relation to the middle of the grid, let's say. So, for example, curves like the blue one, this blue Gaussian. Of course, we have to fit these parameters theta, and I'll explain that in a bit. And then this last block, U, basically translates, so it advects or it shifts the whole wave function by some amount. And so we would get the orange curve here. And this is just for, let's say, to enforce the initial conditions. And then the time evolution of the system through the VARKite algorithm that I mentioned will evolve the system and will lead us, for example, to some final wave function in green that you see here. All right. Maybe this is a good time to ask if there are any questions so far. If that's okay, then maybe I'll proceed. So this was very generic. So the physical problem that we're interested in is, as I hinted at in the beginning, particles in extreme magnetic fields. And it so happens that, for example, if an electron is in a very strong magnetic field, it will have a curved trajectory, and so it will radiate energy and lose energy in a certain way. We're mainly focused on the process called nonlinear Compton scattering. So it will emit a very high energy photon in this case. And The exact details of these equations don't really matter that much. But essentially, if you were to simulate this distribution function in energy, which here is called gamma, the Lorentz factor of the electron, this is a transport equation, which we can simplify further. There's a regime where this can be approximated as a Fokker-Planck equation, which is very close to the heat equation. It just has some additional terms. And there has been some previous work in the literature where people actually simulate these Fokker-Planck or stochastic processes with quantum algorithms. And so these were the papers I based my work on. So we're using essentially very similar techniques to theirs, although a bit tweaked to our specific application to solve this physical process. So the way that we encode the distribution function f on a grid gamma, so we will have exactly like we have with classical codes, we have some grid defining the domain of this variable gamma, the energy. So it can go from the minimal value of gamma to the maximum, and some number of cells. And we choose to encode this distribution function f directly on the amplitudes. There are other choices that could lead to other algorithms, but this is the one we'll choose. And to discretize this differential Fokker-Planck equation, we're using a specific stencil. So to compute this by finite differences, which was used in this paper here. I can explain this in more detail if you want, but this is essentially the equation that we're going to solve, which is this evolution is non-unitary, of course, but since we're using this imaginary time evolution, this is compatible with quantum algorithms. So as I mentioned, we have to prepare some initial state, and we do this classically. So we have some target initial wave function, some Gaussian with some spread and mean energy, and we update the variational angles theta so that the circuit produces this kind of wave function. So we compute some cost function. We try to optimize this with some standard optimizer, either Cobula or something else. And once this converges to a very low value, then we know that we have a good initial condition. Just as a benchmark, we're going to compare these results with a classical code that we use in our group, which at least for the time being doesn't have any quantum computing in it, but we're using it as just as a reference to make sure that the physics is well resolved. And so here are some examples. So you see here that so this is essentially what we're expecting. A Gaussian that with time goes to the left because essentially particles are losing energy. And the spread of this Gaussian also evolves with time in some way. In some regimes, the spread can actually increase at first and then decrease, or it just decreases all along. This depends on the specific physical parameters. But what you can see here is that the full line is from this classical code Osiris. The dashed line is what you would get from solving the discretized partial differential equation classically on a grid, so no quantum. And then the dots are from this variational quantum imaginary time evolution. So the variational approach that we're simulating classically. So we didn't actually run this on real quantum computers, but everything is in Qiskit, so it's QPU compatible, let's say. although it would require many shots and require quite a significant budget to actually run this, and error mitigation and so on. So just to clarify, so of course in practice we would not have access to the full wave function, so we would have to track some observable or set of observables, and here those that make more sense are, let's say, the mean energy and the spread, and you can encode this with the as poly strings very efficiently, so you could measure this on actual quantum computers. So I guess I'm a bit over time or getting close to the time. So just very quickly, this is what you would usually see on these runs. So these are, each line is a variational parameter evolved in time. And of course, by looking at these curves, you cannot extract any, at least I can't extract any physical meaning for why they behave in such a way, just that this is a kind of black box optimization procedure. But our goal was to try to find an ansatz that was actually interpretable. Unfortunately, the only interpretable variational angle or variable here is the mean, because as I explained before, we're actually, this ansatz actually enforces the mean energy. So of course we can attribute a physical meaning to this. All of the parameters essentially collaborate to produce the spread of the Gaussian, essentially. So going back a bit, yeah. So again, we can track this these two moments of the distribution function, average energy and average spread. Fortunately, there are some analytical results, so we can even be more sure of the accuracy of this approach. Here are some other snapshots of the results. And other things that we can, when we have such a Gaussian wave function, are these quantities that of this wave function and the autocorrelation function, which we can compute analytically as well. So these two could potentially be used in the future to track the level of entanglement in the system. Maybe for higher dimensional examples, this could be even more interesting. So just to finish, I'd like to briefly mention that there are these two efforts in our group to which I'm contributing to. So this Replasma is essentially a GitHub repository of Jupyter Mathematica notebooks, where we try to reproduce results from papers that are relevant for our research, namely quantum computing for plasma physics. Of course, not all papers open source their code, but we try to combine many of these notebooks in a single place that is accessible both for students that are new to the field, but also to researchers. And to complement this, there's this living review, which we update from time to time, where we try to put the state of the art of quantum computing for plasma physics, since it's still it's a field in its infancy. It's still possible to track most of the work that is being done, but these two projects are completely open source, and all contributions are welcome. So if you know of some paper that is not on the living review, or some paper that you would like to see the code from in Replasma, then feel free to reach out. You can do a pull request on GitHub. And here are the conclusions to this talk. So basically, so just to summarize, we've simulated this Fokker-Planck equation with this variational approach. We can track some moments of this wave function. And in the future, of course, the goal is to do this in a more realistic scenario, so more dimensions, not just in energy, but all the relevant coordinates, and to apply this to other stochastic processes that could be useful for plasma physics. So I'll leave you with the reference to the paper and the code for this project. And with that, thank you for your time, and feel free to ask any questions.
Thank you very much, Oscar. I would like to start the questions with mine. I think you said that you prepare like the state in a non-unitary way, and then you apply an imaginary time evolution. So I think I didn't understand that correctly. Like, how do you like fix this non-unitary problem inside this like quantum circuit?
Right. Okay, thanks for the question. So if I understand it correctly, essentially, as I mentioned, like both the heat equation and this Fokker-Planck equation are dissipative and non-unitary. We cannot, I mean, so it is what it is. So we have to come up with some mapping to a quantum circuit. There's this paper by Q where they just discretize the differential operators as finite differences, but everything else is what I mentioned. So you exchange the partial differential equation, which is not unitary. It's not a Schrodinger equation in the traditional sense, by a set of ordinary differential equations. So you only use the quantum circuit or the quantum processor to compute. This I should have mentioned more explicitly. These entries for M and V, these are observables that you can extract from a quantum circuit. So essentially, the classical computer would provide the initial guess for the parameters, theta. The quantum computer would be used to measure these M's and V's, and then you would classically solve. You would solve this system of equations that you see here to update the variational parameters, and then you do this in a loop. So you constantly update the parameters, and so you can track, like essentially, you can reconstruct the wave function at any time with this.
Thank you.
Thank you.
If anybody has more questions, raise your hand or just like unmute yourself. I have another question.
Sure.
For the simulations, like I don't know if you mentioned it and I missed it maybe. Like what like do you use like Qiskit or other like software to do the simulations? And of course, these are classical simulations, as you said, no?
Yeah, exactly. So yeah, I'm using Qiskit just with the state vector at this point. So this is still a manageable problem, sufficiently small to actually track all the amplitudes. But as far as I understand, I mean, everything is so Qiskit and NumPy, but everything is quantum compatible, I would say. So we also have, I mean, as I mentioned, these observables M and V. You can build quantum circuits for these. So everything is in principle prepared to run on a quantum computer. Yeah. Of course, there are other packages, but these were the ones that we chose.
Does anyone have any questions?
I do. It might be silly. You might have already mentioned it, Oscar, and I just didn't understand. But could you talk more about how you design the quantum circuit itself?
You mean the ansatz or?
Yeah. That.
Okay. Yeah. No worries. Thanks for the question. Of course, this is uh, as as far as I understand, there are certain problems, for example, in quantum chemistry, where you have some intuition of what is a good you can have some intuition of what is a good ansatz because you know that the occupation levels of electrons in a molecule should obey some symmetry, and so you build an ansatz that preserves that symmetry or something like this. Or if it's a quantum field theory, then you maybe know something about the nearest neighbors interactions or something like this. Here, this is a very general approach. I mean, we only enforce the symmetry at the very end to get a symmetric Gaussian, essentially, that we then translate. But so the only choices that I made was to get the amplitudes to be real valued. So if we had chosen other rotation gates, it wouldn't. And this kind of circular entanglement and so on. I think that you can always play a bit with different ansatz to be more compatible with certain hardware, depending on the connectivity or so on, or maybe you can fine tune like the number of layers to get more expressive quantum circuits at the expense of higher depth or something like this. So I tried some options, and this seemed to be the one that worked sufficiently well for our application.
Okay, could you say more about that? What was it like to figure out which one worked better?
Right. That's a good question. I didn't do this in the most systematic way possible. So I know that there are some metrics for expressivity and there are other metrics to quantify exactly how much of the Hilbert space an ansatz can actually explore, and you could do some parameter scans to and maybe some Pareto optimization to get this optimal trade-off between depth and expressivity or something like this. We tried to do this in an initial stage, but it didn't go to the final version. So I would say that a more systematic approach would be this: to try different different circuits, different ansatz to quantify like exactly how good they can express actually the physics of the problem, and then check some trade-offs. Yeah.
Okay,
Right.
thank you.
Thank you.
Okay, I think we can move ahead. Thank you, Oscar, for this really informative talk. We got to know more about plasma physics and how quantum computing can be applied to plasma physics problems. So I think we can move ahead and for the
Okay, thank you.
presentation on Zotero, and will be presented by Ender. Ender, over to you.
All right, let's move on to this little demo. If you are like me, you may be starting to work on your thesis, or if you're working on any kind of paper and need some help with your citations and keeping track of a bunch of articles. Hopefully, this application is going to be helpful for you. Let me start sharing my, sent a request to share my screen. All right. Okay. You can all see my screen? Yes? Cool. All right. So if you go to sotero.org, you'll be able to download this wonderful application. Before you download it, I do suggest you make an account. You don't need it. But if you plan on using this across multiple devices, it does help keep everything synchronized nicely. One sec. Let's go through this CAPTCHA that I've already failed a couple times today for some reason. Once you're logged in, you can actually just use a web app with it. It does also have a client. Let's go back to that sotero.org so you can see. So you go to the website, you go to download, You'll be able to download a client. It's available for Mac, Windows, and Linux. And you'll also have a connector for your browser. I highly suggest having both the client and the connector set up. Once you have these things set up, you'll have a client on your computer that looks like this. As you start adding articles to it, they look like this. You'll see it gives you everything about it, the item type, the title, the authors for it, the date of publishment, a URL for where you can find it. It's very helpful on how it collects things very automatically for you. Here, for example, this article, it actually contains the full PDF right here. Within the application itself, I can go through it. I can go and annotate actually and keep these for later. I can add notes if I so wish. Hello. I'll come back and delete these later. I can actually even, let's say I'm going through this PDF, through this article about quantum Fourier transforms using dynamic circuits. I'm reading through it. As I go through, I read this sentence about requirements of large-scale quantum computations. It's got a citation right here. I can hover over it, and it'll show me more about it. And actually, I can go ahead and follow the link directly to it. It'll open the archive or wherever else you can find it. If you've downloaded the connector, for example, so I opened the PDF. This over here is the plugin for Zotero. As you can see, it says Save to Zotero. If I click on it right then, it's saying saving to my library, snapshot, full text. Now I can go ahead, open the client again, go back to my library. And if it's, yeah, right there. It actually updates pretty quickly. Fault tolerant quantum computation. I can open it up right here. Start editing it as I wish. Let's see, something else. So you can have the client, you also have the web app. If you are silly like me and like to read on the metro, there's also an iOS and Android app for it. It lets you annotate things as well. It actually already updated. It has that fault tolerant paper on there available. You can also add, it's not just PDFs. You can add books. You can add journal articles, hearings. It'll walk you through giving it all the information that it needs to add it. As you add things, you can also, let me do it from the client actually. As you add things, you can actually attach things to each article if you need a file attached to it, a link attached to it. So you can just kind of keep all of your articles and all of the information that you want to it collected together. As you grow your library, if you're ready to say add this to your LaTeX file, you can actually go ahead and go to File, Export Library. You can do a format, BibTeX, say, okay, test. I'm just going to call this file test, replace the one that's there, go over here. If you open it up, ta-da, all you need to do is go ahead, copy and paste if I don't have overleaf, but just paste if you're using overleaf, paste it to your .lib file and you've got all your citations right there. You can actually also get individual citations from these. If you right click, you can say create bibliography from item. It's got a bunch of different citation styles. I've got AIP style manual 4th edition right there. It's not included by default, but you can do manage styles, get additional styles, and it's got like 10,000 plus to choose from. But yeah, so you say create bibliography, AIP, copy to clipboard, or save as RTF, whatever you like. If you copy to clipboard, you can just go here, paste, ta-da. Let's see, some more interesting things. Oh, there's actually just a zbib.org page that's just for bibliography. So say I want them to give me the bibliography. Oh, one sec. I need that to go away. I just want the bibliography for this archive article. Oh no. All right. It's not cooperating here. But if it were, it asks you what citation style you want, and it goes ahead and spits it out for you to just copy and paste. Um, and then another interesting thing we should go over is groups, which I think it'll be fun for us to set up one. So you can go over here to File, New Group. It basically lets you set up a group that everybody can go ahead and add to. Let's go ahead and create ourselves a DigiQ Journal Club group. You can have them be public or private. Let's just make it public for now. Yep. Just a couple settings you can set for it. And if it cooperates, all right, we've got ourselves a group. Let me go ahead and see if I can share that. Where are messages? I cannot share that right now, but I will share that in a little bit. But now we can all go ahead and add articles to this. So as we are a journal club, we do hope to, in later sessions, share articles that we are all interested in that we can share and talk about here. This is a good place to start putting them in, see what we all find interesting. Yeah, I think that's basically all I wanted to cover. Are there any, oh, one more thing. One more thing, actually. It also does have plugins to connect with other things. This part I don't understand as well, but just so you are aware, they do have a whole plugin library, which I have lost. But if you search Sotero plugins, the documentation's right here. And they have a bunch of connections with other things. They've got like a WordPress section, a Word section, LaTeX. I believe there's something about connecting it to Overleaf as well, but you might need to have a premium account for that. I saw something about a workaround somewhere, but I couldn't figure that out. But if somebody figures that out, please share with the group. Yeah, that's all I wanted to cover. Are there any questions? I think I might have gone real fast, but I can go over anything else if you want.
I think that's no problem because since the recording is gonna be there, I will definitely have to check it again because this is so useful, like to be able to copy all the citations.
Mm-hmm.
For sure.
Yeah. That export function is wonderful. Here, just so you remember where it's at, export library. Ta-da. All right. If there's no questions, thank you for listening to this little demo.
Thank you, Ender.
Thank you, Ender, for this really nice short presentation on Zotero. I think it will definitely help people. And for those who were not able to join, we'll put this recording on our website and they can check it whenever they want. And with this, I announce that this is the official end of the meeting. And thank you for joining us.